Good day, ladies and gentlemen, and welcome to the Cyberseminar's conference call. My name is Tanya, and I will be your coordinator for today. At this time, all participants are in a listen-only mode. We will conduct a question-and-answer session towards the end of this conference. If at any time during the call you require assistance, please key *0, and a coordinator will be happy to assist you. I would now like to turn the presentation over to your host for today's call, Mr. John Duncan. Please proceed, sir.
Thanks, Tanya, and welcome everyone to today's Cyber Seminar. Glad you all could make it. And I'm just going to quickly go over a few background details for any of those of you amongst us who have not participated in this series before. This is the 9th semester of the Cyber Seminars as part of our education and outreach program. If you have any problems today, you can send those in the chat box in the right-hand side of your screen to the host, and you can select in the Send To drop-down menu who you want to send that to. As always, we're interested in getting feedback on this series. That can be addressed to commanager@kawazi.org. And if you do run into any problems today with WebEx itself, this presentation has been uploaded to the Kawazi website, and you can get it there from the Cyber Seminar page. Just one announcement. We've got one remaining Cyber Seminar for this fall. It's 2 weeks from today, and it's Siva Sivapalan from the University of Illinois, who's going to be talking about advancing hydrologic predictability in a changing environment through interdisciplinary synthesis. So that's going to be the last Cyber Seminar for this fall, and again, that's 2 weeks from today. But I'd like to introduce our speaker at this point today. Professor J. Famiglietti is a hydrologist on the faculty of the UC Irvine Department of Earth System Science and Civil and Environmental Engineering. He teaches courses in terrestrial and global hydrology as well as in introductory Earth System Science. His group research uses satellite remote sensing to track water availability on land and has been working for many years towards improving hydrologic prediction and global climate models. Before joining the faculty at UCI in 2001, he was an assistant professor and associate professor in the Department of Geological Sciences at UT Austin. He was also the associate director of the UT Environmental Science Institute. Professor Famiglietti currently serves as the editor-in-chief for the Journal of Geophysical Research Letters and is also a member of the executive committee of the board of directors of Kawazi. Professor Famiglietti holds a bachelor's in geology from Tufts, a master's in hydrology from the University of Arizona, and an MA and PhD in civil engineering from Princeton University. He completed his postdoctoral studies in hydrology and climate system modeling at Princeton and at NCAR, the National Center for Atmospheric Research. Jay's talk today is going to be on terrestrial and global hydrology from satellite observations of time-variable gravity. And Jay, thanks so much for being here. We greatly appreciate it.
Thanks, John. So today I'd like to show you some of the work that we've been doing with the GRACE mission, where GRACE stands for the Gravity Recovery and Climate Experiment. And the we really represents this group of collaborators that you see listed in the PowerPoint presentation. This GRACE is a geodesy mission, and it's designed to measure changes in the rapidly changing part of Earth's gravity field, the time variable part of the gravity field. So since it comes out of this geodesy community, I think that a lot of the things that GRACE enables in hydrology have gone under the radar. We give lots of presentations in GRACE-specific sessions, in the geodesy section at AGU, and so it's not really clear to me that the message is getting out there about what GRACE can do. Some of our key publications show up in geodesy journals and other journals like TRL and EPSL, where that hydrologists don't typically read. So what I thought I'd do today is try to give you a good feel for what GRACE can do for hydrology. It's not the complete spectrum. I'm really only showing results from my group, but I hope that when I'm done, you'll have a better appreciation for what the mission can enable.
Hey Jay, speaking of getting the message out, some folks are having difficulty hearing you. So if you could increase the volume on your speakerphone, or if Tanya, you could increase his volume.
Okay, what I'm going to try to do also, let me switch over. I hope I don't lose everybody, but I'm talking on my speakerphone. So let me increase the volume. Does this help at all?
It does for me, yeah. Thanks.
Okay. Okay. So, as an overview, I'd like to talk about what the satellite configuration looks like. Then move on to how GRACE can provide, given this configuration, how is it that we actually get hydrological information out of a gravity mission? And then spend most of the time talking about the implications for terrestrial and global hydrology, and I split it up into a couple of groups. One is what sort of new information are we getting on water storage and trends on the continent. And then, a big thing that GRACE can do is enable water balance closure. That is, it gives us storage change information that we didn't have before. So we can close the water balance, and when you close the water balance, you can do different things. We can estimate different fluxes. I have some examples here that I'll talk about estimating groundwater storage changes, regional and global discharge estimation, and then I'll finish up with a slide on looking at the whole Earth and water storage changes in the ocean, on land, and in the ice sheet. So how is the audio? Is that okay for those that were having problems?
So Tucson, if you want to chat back, I think it's fine, Jay. Thanks.
Okay. Okay. So what is GRACE? Okay. These are the studies. Thank you. Okay. So what is GRACE? It's the Gravity Recovery and Climate Experiment. It is these two satellites, as you see on the right side of the slide. The two satellites that are in a tandem near polar orbit, and they follow each other around the globe. And the measurement, the fundamental measurement that GRACE makes is a very accurate measurement of the distance between the two satellites. So that accurate monitoring of the inter-satellite distance really forms the basis for mapping the gravity field at monthly and longer time intervals. So it kind of works like this, as we see in this slide. As these two satellites are orbiting around, the first one, as we see in the top panel, approaches a mass anomaly, and it's actually pulled downwards towards the anomaly, and it's accelerated towards the anomaly. And then in the middle panel, you see it kind of starts to drift back to its original position in the orbit, and then the second one is pulled down and accelerated towards the mass of the gravity anomaly, and then as it passes by whatever the feature might be, it relaxes back to its original position in the orbit. And so it's that distance that's tracked by GPS and by K-band microwave ranging, and it is really accurately measured, like to a sub-micron level. The satellites are in orbit that's about, altitude is about 450 kilometers, and the distance between the two is on the order of 225, 250 kilometers. And the inter-satellite distance is tracked to the sub-micron level. So that's pretty impressive. So here's a look at how GRACE has helped improve the mapping of the static gravity field. So there's the two components of the gravity field. The static one, which is controlled by tectonics and mountain ranges and ocean basins and trenches, the major structural features of the Earth. And then there's the time variable part, which is really driven by mass redistribution. And I'll talk about that one in a second. So in terms of improving the static gravity field, we can see these three panels. The first one is really pre-GRACE. The second one is after 100 days or so of GRACE data. The third one is after about a year of GRACE data. The science team, I was just at the science team meeting in Potsdam a couple of weeks ago, and it was either GRACE Gravity Model 3 or 4 that's even better than these. So you can see real significant sharpening up of the features of the static gravity field. So how does that help us with the time variable component? So imagine that you could make monthly get monthly maps like that of the gravity field like you just saw. If you could difference that, that would give you the time variable component. Turns out that the time variable component is really driven by mass redistribution in the Earth system, and far and away, the largest contributor, or the single largest contributor to the mass redistribution is water mass redistribution in the atmosphere, on land, and in the ocean. So imagine now that we're interested, because we're hydrologists, we're interested in a water storage change on land. What GRACE shows us is this little schematic I have on the right. What GRACE has gives us is the total change in water storage in the atmosphere and on land. There's other things that contribute to mass changes like earthquakes, but those are much smaller and usually have to be sort of teased out of the data to actually see it. So really water is the main contributor here. So GRACE gives us the total change in water storage, and if you want to isolate the dark blue box, the land water storage change, like it's shown in the equation below, we have to subtract off the atmosphere part. We get that from numerical weather prediction models like UCMWF against that NCAR, and we can quantify the errors in that. It turns out to be pretty accurate, and the accuracy is on the order of 1.5 centimeters of water storage on monthly time scale for areas that are 200,000 square kilometers or greater. So this is not, I have a slide coming up that that points out, this is not a hydrometeorology satellite. It's about hydroclimatology. It's about longer time scales and larger spatial scales. Okay, here's my reality check slide. So exactly what I just said. It is, let me just check something here. Okay, I skipped over this slide. I'm sorry. Skipped over slide number 10. Excuse me. So, a couple more points. What GRACE gives us in this delta S land is all the changes and all the water stored on land. So it's all the snow, all the surface water, all the soil moisture, all the groundwater, again, at monthly and longer time scales. So we call that, in our work, we call it either total water storage or terrestrial water storage. If you want to decompose that signal into its components, like I show in the equation at the bottom, then you need more data. So if you want to isolate, for example, the groundwater storage change that we see, we try to use my pointer here. If we want to try to isolate this delta SGW, then we have to subtract all of these guys from the delta S land, which is what we get from GRACE. And I have some examples of some different applications where we've tried that. So here's the reality check again. It's not hydrometeorology. We're not talking about high resolution, fast time scale. We're not talking about 50-kilometer grids. We're not talking about 10-kilometer grids. We're not talking about 250-meter MODIS type stuff. Likely, our expectation of soil moisture is in the tens of meters. It is slower time scale, monthly and longer, and lower resolution, 200,000 square kilometers to continental scale. In fact, the bigger the scale and the longer the time period, the lower the error. Okay, so how do we know that these data are right? It actually turns out to be kind of a challenging thing because, as you know, we don't have a lot of water storage data available to us in hydrology. Excuse me. But where we do look, we see good results. So we've done things like compare the GRACE storage changes to the storage changes that we get from a couple land, atmosphere, and water balance. And it turns out there aren't that many places where you can do that are large enough, and this also have the stream flow data that you need to compute the storage tank. And we've done it basically in every basin. There's only about half a dozen basins where you can do that. Globally, we've looked at those. As you know, there are very few in situ networks that we can use to compare to observation. And so we've compared to Illinois, we've looked at Oklahoma, and then my former student, Aaron Berg, has set up a a satellite validation site up near University of Guelph, and he's been doing some validation work. So I'll show you some of those. So here we have some couple land atmosphere water balances for some of the Arctic river basins, the land of the Ob, the Yenisei, and the Mackenzie. And the black line is the Great Delta S, and the dashed blue and the dashed red lines are our Delta S that we, the dashed blue and dashed red lines are the ones that we compute from a couple of land atmosphere water counts. And so, you know, they're not perfect, but they're pretty good. They track each other well. They're the same order of magnitude. You know, these two in particular look pretty good. We've done it in the Amazon. We've done it in the Mississippi. You know, they all look about the same. They're never perfect, but they're always pretty good, and they seem to be doing the right thing at the right time. We can also look at terrestrial water balances. The reason we go with a couple land atmosphere water balance is because we don't have to worry about estimating evaporation. So we wanted to look in the Colorado River Basin, and so we actually did both. We compared the great storage change, which is shown in red, to a terrestrial water balance, which is shown in blue, where we estimated the evaporation. Actually, we took it out of the reanalysis model, and then to the land atmosphere water balance, which we see in green, and you know it doesn't look as good. And so we're trying to figure out why. It's not all, like I said, it's not all beautiful. Sometimes there's problems, but by and large, many of the places we look, it's pretty good. Here's some in situ data. There are, like I said earlier, there really aren't that many places where you can go and get in situ data, and we all know about the Illinois State Water Survey data set that has very good soil moisture and groundwater, and you can get snow and surface water data as well. So here in the upper panel is a comparison of the gray storage change in blue compared to the in situ storage changes that we compute from the observations, and that's shown in red. And the bottom panel is from this new site in Saskatchewan that Aaron Berg has set up, and this is some work that Aaron is doing with Sean Swenson to try to compare the observed, the in situ change, observed in situ change, the grace change. Sorry for all the different lines here. The grace is in red, and the observation of the total change is in orange. You know, again, it matches pretty well. Now, another thing that we can do if we want to look at the global scale is compare to global models. You know, it's not optimal, but those of us who are interested in larger scale modeling and larger scale analyses know that there aren't many data sets out there. So in a sense, we're forced to do some comparisons to global models. And so we worked with Matt Rodell, who is my former PhD student, who did all of the pre-launch feasibility work for his dissertation. And so Matt's now at Matt Goddard, and he's in charge of the global land data simulation system. So we use the GLDAT, which is a nice modeling framework because it can accommodate several different land surface models. And so we take outputs from the model, but to compare that to GRACE data over the same time period, you have to process the data in the same way that you would process the GRACE data. So you have to convert the model output to gravity field coefficient, process it like you would the GRACE data. I'll show you on the next slide. The comparisons are good, and again, they're not perfect, but they're pretty good. And I have some reasons here for why they might be different. Well, you know, land models don't have all the sometimes they don't have great snow, sometimes they don't have great groundwater. There's no water management in there. So, you know, it depends on your perspective. Some people feel that the GRACE data are, you know, we should be tuning our models to the GRACE data. I'm more conservative. I think that there's problems on both ends. But certainly there's information in the GRACE data that we know is not in the model. Here's a comparison of seasonal storage changes from GRACE in the left column, and seasonal storage changes from GLDAT. I think this is with the NOAA land surface model on the right. So if you just compare left to right, you know, those are pretty pictures, and they're doing the same things in the same places. But the one thing, if you look carefully at it, that stands out is that the amplitude of the gray signal is bigger than the model signal. And the modelers think that maybe this is an indication that, you know, there's no groundwater in there. If you add the groundwater in, it will fit better. The snow isn't good. There's no surface water routing. So anyway, it's food for thought. It is another data set to which we can compare. Okay, here's my heavily biased opinion of the GRACE data. There's really no other way to look at global water storage changes and global water mass redistribution, not just on land, but in the oceans and for the ice sheets as well. So here is, you know, one satellite that can kind of see the whole water mass redistribution picture. So GRACE is a unique mission in that regard. Where we compare to the in-situ data and to the model, you know, the comparison is generally pretty good. And what we see is most often intuitively correct. The GRACE data is behaving in the way that you think it would. It follows what the data is doing. The orders of magnitude are, you know, about right. The seasonal signatures are about right. So I'm pretty comfortable that what we see from the GRACE data is real, and that actually has quite a high information content. And we continue to try to do more validation stuff to push the envelope. We're trying to get down to smaller scale. Recently, we've been looking at the western U.S. I showed that Colorado slide, and we're trying to focus on, most recently, taking a look at the Sacramento, San Joaquin combined drainage and trying to figure out what's going on there. Okay, so what are some, oh, you know, I realized that John and I had a discussion earlier about to have a nice animation of the GRACE data and what they look like. And it just wasn't going to work out well in this web seminar format. But if you want, not that I'm encouraging you to be at all distracted from this presentation, but if you wanted to see right now while we're talking what the GRACE data look like, you could go to this web page. It's just grace.jpl.nasa.gov. And I have that, it's at the end of the presentation if you want to check it later. It's grace.jpl.nasa.gov. And if you go to that page, you'll see the animation right on the front page that I wanted to show you. And I just want to make the point again that the data are kind of low resolution and it looks kind of blobby, but actually turns out that there's a huge amount of information there. So if you want to go take a look at that animation, you can see what I'm talking about. But you can kind of see it in this slide too. So this is the slide. So now we're getting into the sort of the so what part for hydrology. We have the data. You know, it looks like it's a good match to observations and to models. But now, what are we going to do with it in hydrology? So one of the first things we can do is just look at the storage changes themselves. And we've never really had this kind of data before. So we can now see, we've got 4 or 5 years of data, we can now start to see the map on the left shows the spatial distribution of the annual amplitude, the amplitude of the seasonal cycle. So we can see where the signals are the biggest. And on the right side, excuse me, we can start to see the trend. And I use the word trend loosely. I would maybe refer to them as emerging trends. If we had 20 years of data, maybe we could call it 50 years of data, maybe we can call it trend. So we can start to see what's going on. And I think that's maybe the most important point, is that we can start to see these variations in water storage, how big they are, how they're changing over time in a way that we've never been able to do before. So this is really a first look at the magnitude of the water storage variation. There's some very important information in here about places that are gaining water mass, like those shown in yellow and red, places that are losing water mass, like, of course, the ice sheets, the Alaskan glaciers. There's stuff going on here in the Congo River Basin and Southeast Asia. It turns out there's a lot of information in here. And it's stuff that isn't, it's not all straight climate stuff. There's a human signature here as well, and it shows up pretty strongly. For example, our colleagues in Colorado, Sean Swenson and John Ward, have been looking at this mass change signal in the Congo Basin, and they think that it's reservoir releases from Lake Victoria. We and others are looking at the signature of groundwater mining in different regions around the world. Reservoir storage is showing up on here too. So it's a mix of both anthropogenic and natural, anthropogenic influences and natural variation. So some of these trends are starting to emerge, and I'll show you in the next slide what they start to look like. And, you know, on the modeling side and on the understanding side, they're ripe for starting to interpret variations in hydroclimatology, as well as for data assimilation and for pointing to enhancements to models. Here's what some of these trends look like. So I just took that map that I just showed you, the trend map, and mapped it to some of these different basins here. These are all, of course, on different scales, so I apologize for that. And what really captures most people's attention is not the basins that are gaining water, but the basins that are losing water. And so we see the African basins are in this short time frame. The emerging trend is one of a loss. So again, the point is, you know, we're starting to see these ups and downs, and we're able to monitor them and to compare them to data on the ground in a way that we haven't been able to do before. You know, that being said, the Africans and the Australians certainly take great interest in these sorts of figures, and we showed some of these at AGU. Here's a view on a continental basis. We showed some of these at AGU, and we get a lot of attention from the African and from Australian press in particular, wanting to know what was going on and could we convert these numbers into things that they understand in terms of cubic kilometers of drinking water. And they're quite concerned. So they're very interested in what this mission can do for them. These are just some of the numbers. If you want to go back and look, they're in the presentation. There's the basis that I showed and for the content. Okay. Now, for many of us in remote sensing, groundwater remote sensing has been kind of a holy grail, and at the same time an extremely challenging problem because it's underground and you can't really see it by satellite. And so, this mission gives us a nice opportunity to try to tackle the remote sensing problem because, you know, another way to think about GRACE is it's like a giant space-based light-seminar. It's essentially weighing water mass stations. So to get at the groundwater problem, we have to do what I've shown here. We can write the water balance on a storage basis, not on a flux basis, for the land, as the total storage change is equal to the sum of the components, the snow, the surface water, the soil moisture, and the groundwater, can rearrange itself to the groundwater. In other words, get this part from GRACE, the delta S land from GRACE, remove all this stuff, or this stuff has to come from other data, in situ data, model data. Again, shown in the schematic, same thing. If you want to isolate groundwater, storage change, we have to strip off everything else. The atmospheric part that I told you about earlier, as well as now all the water mass above the water table. In the next few slides, I'll show you a series of applications where we've done this. Go from large scale to small scale, starting at Mississippi River Basin scale and getting down to the scale of Illinois and Oklahoma. But also each time we've kind of refined our technique for how to remove this, how to remove that unsaturated zone signal. So in the first one, this is one that Matt Rodell led. We looked at estimating the groundwater storage change for the whole Mississippi River Basin. And we used the GRACE, so we took our delta S land from GRACE, and we needed to subtract off the snow, the surface water, and the soil moisture. And for this application, the Mississippi River Basin used output from the Global Land Data Simulation System with the NOAA model as the land surface model. And so we moved that from the gray signal and compared that to observations, which are an average of 58 wells, shown here, the black line. And Matt did a nice job of getting all the specific yields, used data from the HCBN, got all the specific yields, figured out as best as he could what the storage changes were, and then compared that to so these observations of the storage changes shown in black, and the gray estimates, the gray minus the model, surface water, soil moisture, are shown in the horizontal line here. And so, again, it's not perfect, but there's certainly a coherence there. There's a nice tracking of the grace-based estimate with the observation. The next panel is an application that we did in Illinois. So now we've gone to a much smaller scale. We're right about at the threshold of the 200,000 square kilometers. And those of you familiar with Illinois know that there's the Illinois State Water Survey, the whole data set that's there. And so we were able to compute the observed or estimate or put together an estimate from observation of the statewide groundwater storage chain. That's shown in the red dashed line. And compare that to the gray data with the observed soil moisture and observed snow and observed surface water, not modeled this time, but observed, subtracted from the gray signal. And that's the result. So the blue is the gray state estimate, and the red is the observation. And this is the seasonal cycle. Again, it's not perfect, but they're doing the right things at the right time, and we feel it's pretty decent. Considering the challenges of groundwater remote sensing, we feel that's pretty good. Last application that I'll show you, or sort of test problem, is in Oklahoma. This is one that Sean Swenson led. Sean's at NCAR. Now he was the student of John Ward, so really these guys are real experts in great data processing. And so what Sean did here, is the thing that's distinctive about this application is that he did a very nice job estimating the moisture content in the whole soil moisture profile. In our Illinois application, we kind of fudged it between the 1 meter, the lowest measurement point, and the top of the groundwater table. We just did kind of linear interpolation. Some did an empirical fit, so he did a nice job using observations of removing that whole untapped sun signal. So what we see here is the grace-based estimate of the groundwater storage chain. So it's grace minus the surface water minus his estimate of the soil moisture chain. Turns out there are not that many wells in Oklahoma, but he got what he said it was only a handful, and those are shown here. And then the two are put together. So it's the comparison of the grace-based estimate of groundwater storage chain to the observation. Just in text here, the method will soon be applied where groundwater is not well monitored, but depletion is likely in northern Africa, the Middle East, and so on. Well, of course, all that depends on funding, but certainly there's a lot of interest, especially in the developing countries. I want to switch gears now and talk about discharge estimation. Many of you know that there's big interest in the hydrologic community in remote sensing of surface water discharge using altimetry. In fact, there's a working group that I'm a part of that is really pushing for a hydrology-specific altimetry mission, and that's great. What that would do would really give us a picture of the land surface inundation by water, so water coverage and its seasonal variation. It would map surface water height essentially, slope, inundation extent. And so it's kind of mind-boggling that we don't have that information currently on a global basis. But this mission would certainly help us achieve that goal. This is a different approach. It's a complementary approach. It's a math where we're going to solve a mass balance again. We have delta S from grades for water balance closure. We're going to solve a water balance equation here for discharge, and it's a very complementary thing to what we're talking about with the altimetry. Why do we want to do space-based discharge anyway? Why can't we just go gauge it? So as many of us now know, the number of stream gauges is in decline globally. Gauges don't really measure, sometimes don't measure the full flow anyway. They don't, cannot capture flow in floodplains, in braided channels, in wetlands, and submarine groundwater discharge. Where gauges do exist, this is true for a lot of international data, where we do have data, whether it's stream flow or groundwater or whatever, there is inadequate international data sharing. The data holdings can be fragmented. There's variations in formatting and data quality and so on. So in short, again, this is true with a lot of hydrology. There's really no comprehensive near real-time observing system, in this case for discharge. So it can be remote sensing in context of this stuff. The grades play a role. So this is how we approached it. You could use the terrestrial water balance as shown here and rearrange and solve for discharge. The problem, again, is the one with evaporation. We don't really know it. So we get by the T minus E, or particularly the E problem, by going to the atmospheric water balance, coupling the two, rearranging, and then solving a coupled land-atmosphere water balance for discharge, where we get the delta S from grade, and these are atmospheric moisture terms, the precipitable water storage change, and the horizontal water vapor diversion. Now, what's nice about this stuff is that people have applied this before. So if you go and read the papers on global discharge, people have applied this before, but they assume, since we haven't had delta S before, they assume that delta S is equal to 0 and apply it on annual timescales. So in other words, they're assuming there's no land water storage change on annual average. Well, it turns out that, at least for the grade time period, that's not true, and there's really no reason that it should be true. As ice melts and some of that water goes in the ocean, some of it ends up on land. There's really no reason why to assume that the delta S is going to be equal to 0. So anyway, we previously had to assume that delta S land is equal to 0, apply the equation at annual timescale. Now we don't have to do that. So we can do monthly time series. The other nice thing about this is that it's given us the total basin discharge. It's all the surface water flow, it's all the groundwater flow. It's the net basin discharge. Okay, so here's what some of this stuff looks like. And so the next few slides, I'll take you from small scale to large, or relatively great small scale, basin, big basin, to drainage regions that drain into the ocean, to continents, to the globe. So we have applied this at several of the large river basins. I show you the Lena River Basin here. Black is the observations. The red and blue lines are our grade-based estimates using either the ECMWF, atmospheric moisture curves, or the NCAR. It looks pretty good. There's differences. We think we can explain the differences. We've looked at about half a dozen large river basins where we can get discharge in near real time, and for the most part, they're pretty good. They're different. We think we can explain the differences. There's only one, I think. I can't remember which one it is. It's really bad. I can't remember which, but it's one of the Arctic basins. I can't remember right now which one it is. This is a paper that just came out in GRL, by the way. So anyway, having looked at several basins, we then go and scale up to or apply the method to the whole method. So I don't think it shows up that well on this slide here, but the land region that drains into the Arctic Ocean, and that's shown here, and for ECMWF or NCAR based estimates. And so that's kind of cool because before this, there's really no other way to do it except by modeling or taking gauge data, and most of, or a big chunk, maybe, I don't know, 25 to 33% of the Pan-Arctic is ungauged. And I don't know what the number is globally, but this is a method that allows you to apply the techniques globally. What I've shown here is just a comparison. We tried to do a sort of apples to apples comparison of our numbers, and here's the average of our number down here, our numbers down here. And we tried to compare to another study that was primarily, if not completely, observation-based, and for the same time period. This period of those discharge estimates were 2003 to 2005. There's only one in this list, and that's the McCollendale number. And when we scale it up, so they didn't do the whole Pan-Arctic, but when you scale it up to the region of the whole Pan-Arctic and project it forward in time, this is the number that they get, the 3238 cubic kilometers per year, and our average number is 3588 cubic kilometers per year. And there's a difference, and that difference is significant. It's about the size of the ice mass lost from the ice sheet. So our conclusion from that study was that perhaps the discharge is bigger. If you believe the method that we use, perhaps the discharge is bigger into the Pan-Arctic than could be expected from just scaling up gauges. So maybe there's an acceleration, and time will certainly tell. The next couple of slides just show the same approach, just applied at larger scale to the other drainage regions. Here's the Pan-Arctic, the Atlantic, the Pacific, and the Indian Ocean. Again, those are in different scales. I'll show you a comparison in one of the next slides. And we're starting to look at the, why the magnitudes differ, why there's phase differences. And the next slide shows the discharge per continent. Same thing, they're plotted at different scales. Let me show you, I think it's the next slide that shows the relative contribution. And so there's nothing real new about this stuff. What's new is the estimates themselves. In terms of the relative magnitude, there's no surprises. You can see this sort of thing in textbooks. But it does confirm previous estimates, and we think it's a nice contribution to the global discharge effort. These are just some comparisons to other studies, which I will skip over. This slide, what we wanted to do here was do a semi-independent check. We've been doing most of our discharge estimates as estimates of discharge off of the land. So land-based, we do the coupled land atmosphere water balance and estimate the discharge as a loss from the land. But you can do the same thing on the ocean side. You can do your coupled land atmosphere water balance. Now you use the delta S, the ocean mass change. Use your atmospheric moisture curves over the ocean, and you solve for runoff as an input into that. And so that's what this is. It's sort of a semi-independent set. And the blue line is the ocean when you compute the discharge as input into the ocean, and the red and the green lines are basically two different takes on our land-based approach. And they actually agree pretty well. These are seasonal cycles, so when you average it over the year, they are very close to each other. I don't have the number here, but it's like a few hundred cubic kilometers per year. They agree nicely. They're both within the range of previous estimates. There's a little trend there. And I don't really want to talk about trends so much because there really aren't enough data, so I'll skip over that part. But the bottom line is we're pretty comfortable with this approach, and what's nice is that we can get monthly time series. Let's get what some of the global numbers look like if you want to go back after the talk and download the presentation. Some of those numbers are there. This is a paper that we're just about to submit to Journal of Hydrometeorology. I want to finish up with a look at some fully global mass redistribution. So we can look at all the water mass now and how it's changing. So what do global land water storage variations look like How do they compare to the ocean and to the ice sheet? What are the trends that are emerging? What are the magnitudes of the, the amplitudes of the variation and so on? We do that all now with GRACE, and this is what it looks like. So let me walk you through this slide. The red line is the, now these are anomalies. Most of the slides that I've been showing previously were DSDT, monthly storage changes. These are actually anomalies. These are differences with respect to the average over the time period 2002 to almost the present. And so the red line is the ocean mass change, and the blue line is the land mass change. That's without Greenland and Antarctica. I think most hydrologists, anyway, probably are unaware of this exchange between the land and the ocean, the magnitude of it. They're basically 180 degrees. They're almost perfectly out of phase. So there's this huge trade-off of water between the land and the ocean that's just the workings of the water cycle. That's the precipitation, the evaporation, the runoff, moving the water and vapor transport, moving the water from one of these giant reservoirs to the other. We also have the ice sheets on here. So Greenland is in green, and Antarctica is in gray color. And so right away you see that the amplitude of the land-ocean exchange is way bigger than the ice sheet change. It really dominates the variability that we see. We do have some of the trends listed, and so these are right in there with the current Greenland and Antarctica trends. And what's interesting, and of course we expect the ocean mass to be going up, and a lot of that water from the ice sheet winds up in the ocean, but not many people have really been thinking about what's happening on land, and it turns out over this time period that this, again, emerging trend is a positive one. So the message is that, not all of that water, and there's no reason why it should be this way, not all of that water from the ice sheet that now just sits there in the ocean, it evaporates and becomes an active part, and basically becomes active in the water cycle. So that there's a positive trend here. It's about the same size as the Greenland trend. So I think the unknown in this global water balancing has been what's going on with land. The GRACE mission has helped us see that. This also has, of course, huge implications for global mean sea level rise. So I believe that's my last slide. So I will summarize and try to answer some questions. Hopefully today I have demonstrated the importance of GRACE as a component of a global hydrological observing system that can help us characterize water storage variation, groundwater storage. I didn't talk about evaporation, but we've used it to solve the terrestrial water balance for evapotranspiration, groundwater, regional and global discharge. We'll continue to try to push the envelope on application. We're interested in working on snow water equivalent, and I started talking to Jeff Dozier and his colleagues about that. Drought. I don't do much of the data assimilation myself. I would put myself more in the constraining model simulation. I mean, we compare what our model simulates to what GRACE is doing, but we're not trying to do formal assimilation in micro. Having made good progress on some of these concepts, approving some of these concepts, now we want to get into some of the strengths. Now we can start to see the seasonality in the discharge and the seasonality in the water storage tanks. So we need to start to understand them in terms of some of the different oscillations that are part of the climate system. So how does water storage record the climate oscillations? Are there lower frequency feedback to climate? How can the emerging trends be explained in the context of climate variation? Is there an anthropogenic fingerprint on storage? I believe that there is, and that we're already starting to see it. What are some of the implications of the discharge data for ocean circulation? Can you take those discharge estimates and put them into a global ocean model and see what happens, see how it changes the ocean circulation? I think that these data can help us further refine our concept of how land, water, ice, and the atmosphere exchange water. There probably are implications for acceleration of the water cycle. If you go back and look at that last slide and think about the amplitude of those storage change signals. And I mentioned just briefly the contribution of continental water storage to global mean sea level, the direct implications for that. So I will finish up with just one last slide which shows you where you can go get some of these data. This first one is from my group, and we have things split up by watersheds. We have global maps, we have watersheds. We have a lot of ancillary data there that you can use to do basin scale water balances. And then the main data portal for GRACE is called the TELUS, TELUS site, which is a NASA Reason project. That's just the address here, grace.jpl.nasa.gov. So there's lots of data there as well as animations that you can start to take a look at. So that's it. I want to thank everybody for listening in, and I'm happy to take any questions.
Jay, thanks so much for a really fascinating talk. And Tanya, are you there?
Yes.
Can we open it up for questions?
Sure. Ladies and gentlemen, if you wish to ask an audio question, please key *1 on your touch-tone telephone. You may begin by pressing *1 at this time.
And you can also type them into the chat box, and we can get them there as well.
We have a question from the line of Richard Hooper. Please proceed.
Hi, Jay. Thanks for the talk. Just a quick question on that final slide. Here's a hydrologist. I didn't worry about this large seasonal exchange between ocean and I guess the amplitude there, if I'm lining up everything correctly, is annual. You have a positive and negative. So I take it's because of the differential of land mass from the northern hemisphere to southern hemisphere that it's not even. That if in fact we had an equal amount of land area in north and south, then you wouldn't see this amplitude, or am I missing something?
I don't know, Rick. No, I don't think that. I'm not sure if that has any implications. I haven't really thought about it. I think that the amplitude. I just started thinking about this actually before. I mean, this is all new stuff, obviously. So I just started thinking about this when I was going over the slides for the presentation. I think that as more water melts from the ice sheets and ends up in the ocean, that we're going to see a bigger amplitude. So I would expect this amplitude to increase.
Okay, so that's maybe I said the wrong word. Not amplitude, just the fact that we have a cycle. If there were equal land on the north and the south, wouldn't you expect there to be no cycle? I'm just trying.
No, I don't think so. It's tricky stuff to think about. But
okay.
I know I'm going to see you Monday, so
I'll talk about it
on the plane. But intuitively, I don't think so. I think this is more just a measure of the water moving around from land to ocean and back again.
But it has to do with the seasonal cycles, obviously, right? It's an annual cycle.
So I need to think about it.
Okay, very good. Thank you.
Sure.
Our next question comes from the line of Matt Davis. Please proceed.
Hi, Jay. Matt Davis here.
Hey, Matt.
Are the fluid temperatures recorded?
Well, certainly it's not something that GRACE is going to see. Okay, so GRACE is going to see mass changes, and I don't think that's not temperature, not temperature dependent. It's not going to affect the measurement. We would affect, scientifically, the speed of the exchanges.
I was thinking the volume. I mean, if you're estimating the mass from GRACE,
yeah,
you're interested in the fluid volume.
Right. I don't think so.
Okay.
That's a good question.
Right. Nice talk. Enjoyed it.
Thank you.
Thank you.
Ladies and gentlemen, as a reminder, if you wish to ask a question, please key *1.
So Tom, over, I see that you're thinking the same thing as Rex. I have to give that some thought. I hadn't really thought about it.
And Mr. Duncan, I show no audio questions at this time.
A shy group. So, Jay, just one question for you. You mentioned that you're trying to push the envelope in terms of moving this to smaller extents or smaller river basins, and you mentioned towards the beginning of your talk doing something in the Sacramento-San Joaquin.
Yeah.
So isn't that, I guess I don't know the drainage areas as well as I should of my California river basins.
Yeah.
But that's quite a bit smaller than...
Yeah, it is. And so that's what I mean by pushing the envelope. And in fact, when we do the comparisons, like a lot of the stuff I showed where we compared to observation, you know, actually things look pretty good. But once you start going down to the smaller scale, timing is good, but the magnitude goes off. So, you know, we'll see what we can do. There are some groups that are working on higher resolution processing, both spatial and temporal. So that will probably be the direction that we go. That stuff is really more in research mode right now. So, but that's probably the direction we're going to have to go.
Okay. Is anyone working on, even if they're in a smaller basin, using GRACE type of data to set the context and at least initiation of storage parameters for whatever surface water or groundwater models they're using? Do you know any work in that area?
A lot of, I mentioned I was at the GRACE Science Team meeting, and a lot of what was discussed on in Europe, there's a lot more interest in using GRACE for model calibration, for comparison, for initialization, than there is here. The scales at which they're doing it, I think they are going down below 200,000 per kilometer. We really try not to do that because you know, we kind of know that the error goes way up.
Then I see that Ted and Jenny from SUNY ESF has a follow-up on are there plans for finer spatial scale gravitational measurements?
So there's the space-based side and there's the ground-based side. On the ground-based side, I don't know. And again, I think the Europeans are much more interested in doing that, and I think they actually have some fairly ambitious efforts going on. On the space-based side, that would be the GRACE follow-on mission. And as I'm learning, it's quite a competition to get a satellite mission selected. Never mind, reselected. There was the recent NRC decadal survey, and GRACE was one of the 7 or so missions that was highly ranked. GRACE 2, the follow-on. And I believe that would go down to under 100,000 square kilometers. So, but that's like the 2015 time scale.
Okay. And so how long will GRACE be up for collecting data in this current mission?
Yeah, I mean, it's been a few more years. It's actually past its nominal lifetime, which was 5 years. But recent estimates are like 2012. So apparently it's going to be going for a while. And so that's good news because it will help us extend some of these time series and differentiate, variations from trends and so on.
Great.
We do have an audio question, sir, from the line of David Tarbottom. Please proceed.
So I was looking at the seasonal cycle graph and wondering if there's any correlation between temperatures. It may be that warmer years you get more precipitation that falls on the land, so there's a correlation there.
Yeah. So I don't know, Dave. I mean, it's all wide open stuff. So this is sort of hot off the press, and that's why I had that long slide of sort of like the science stuff. So what we've been doing for the past couple of years is really sort of demonstrating the capabilities, and now it's time to start doing some of the science. So excellent question. We need to understand what's going on and why. But yeah, I mean, I think there has to be a lot of it. There's going to be two things. There's the activity of the hydrologic cycle, as you said, whether there's more rain or less rain, and what those variations are. And then you've got to factor in the ice sheet stuff too, sort of slow, steady contribution of more water to the ocean, and where that water ends up. Okay, so here's some other questions here. Let's see. Other questions. That was Ted, Gabriel, Sinead. Could this be useful for seasonal rainfall forecasting? I think the way that it would be useful would be if it were assimilated into a forecasting model and used to constrain the total water storage in a large river basin system. So it would just be a large-scale constraint. So in that sense, yes, but it's not going to be like high-resolution flow moisture kind of thing. Ted, does anthropogenic influence on GRACE observations include change in non-hydrologic mass buildings, other stuff? So all that stuff is in there, but it's in the noise. It's in the noise level. So it's pretty low. Erosion. The thing that I always say, and it turns out to be quite true, is that water is really heavy, so it's really dominating the signal. But you can see things like earthquakes, buildings. I have my doubts, but large-scale movements or mass movements, whatever they're going to be caused by. The number one thing is water, earthquakes, slower time scales. Volcanoes. I haven't actually thought much about volcanic stuff, but I have to check with the rest of the science team on that.
Mr. Duncan, we do have an audio question.
Okay.
Comes from the line of Ted and Dreamy. Please proceed.
Hello. I did not know I had an audio question in, but if you can hear me, Jay, I wanted to thank you for the talk. It's fascinating.
Thanks, Ted. And so you just heard my answer to your question, right?
I did, and I appreciate you identifying erosion and volcanic activity as more likely. I agree that a single building wouldn't make an imprint, but if you had, let's say, this urban fringe in developing country over several years, I wonder if that might end up registering and creating a change in storage.
No, so we can do the calculations and compare it to, water, groundwater storage change and over a large area, and compare that to the mass of the building. That's the way you get your answers. Another thing that I didn't mention, Ted, that we have to factor out of this stuff is post-glacial rebound. So that's actually something that comes into play on these time scales. And in particular, when you're up there looking at Greenland and Antarctica, you have to worry about rebound, and that's not my area of expertise, and that's why this particular project is one that the slide that we're looking at is collaborative with geodesists who actually have a pretty good handle on that stuff.
I want to follow up, I guess, now that I'm online with you. The insight you gave me, mentioning the holy grail of observing groundwater, I agree that would be ideal. And your illustration showing how we might go and actually sense the surface moisture storages and then back out what is the flux in that aquifer is something that I hope to see the team that's listening today push forward and demonstrate.
Yeah, and I think that there's a lot that can be gained. So we're not a groundwater modeler, but if people want to try to combine this with groundwater modeling, with INSAR for the changes in the the aquifer characteristics, eventually we're going to have soil moisture from the SMOS or whatever eventual sensor. So over time, I think we're going to get more and more pieces of the puzzle to be able to do it better.
Thank you again.
Sure.
Okay, last call for questions.
As a reminder, you may key *1 to ask an audio question.
Well, while folks are debating, I think we're at 10 after the hour, so we should be wrapping up. But Jay, thanks again for a fascinating talk and for throwing up such a provocative slide at the end here. Give us all something to cogitate upon over the weekend, for sure.
Thanks, John.
All right. No other questions, Tanya?
No, Mr. Duncan.
All right. Well, Jay, thanks again. We really enjoyed it.
Okay, guys. Thanks for listening in.
And the next one will be 2 weeks from today by Siva Sivapalan. We'll see you then. Take care, everybody.
All right.
Hey, Jay, do you want to stay on the line for a sec?
Sure.
This concludes the presentation. As a participant, you may now disconnect and have a great day.